All right. Today we are going to take our first peek into what is called Phase Doppler Particle Analyzer, which is PDPA. These lectures are also taken from Professor Cameron Topia's book, as well as his lecture here at IISc. So he's one of the pioneers in the PDPA technique, as we all might know. So PDPA, we have done LDV already. We have done all these lectures on light scattering and stuff like that. So the PDPA will be a little bit, what do you call, easier comprehend with that particular background. So without wasting time, let us go and see. So again, we are just going to spend a few minutes on the review of light scattering from spherical particles, and then do the principles of phase Doppler measurement technique and how the phase Doppler technique is realized, standard system, planar system, or dual mode system. And we are also going to take a sneak peek at interferometric particle imaging as well. So the measurement techniques for droplets, as we know that the droplets form a fundamental fundamental piece in most of the applications, because most of the applications are multiphase, and multiphase usually involves droplets in one way or the other. So there are direct measurement techniques which measure size, velocity, and shape, which is like PDPA, which is like PIV, shadowgraphy, and clear point separation. We will see what that means. And there is also intensity and intensity ratio. So there are like extinction based measurements, like Rayleigh extinction measurements. There is also Me and LIF ratio, 2-band, 3-band. LIF is laser induced fluorescence, stuff like that. There are interferometric techniques like laser Doppler and phase Doppler and eyelids, which is basically the content of this particular lecture. So the measured quantities are size, velocity, refractive index. There are time shift techniques which are also available, which also measure size, velocity, and there are pulse delays, and then there is Raman scattering used for Raman spectroscopy. Because of the specificity, Raman is a highly utilitarian method, but it has got very low signal to noise ratio. So it is also used for temperature and species concentration measurements. So there are a lot of diagnostic tools that are available in the community, where you can measure different things like temperature, size, velocity, and so long and so forth. So this you have already seen in our lectures, that when there is an incident plane wave which interacts with a particle of homogeneous material, it basically scatters in all possible directions. And the exact solutions of these problems are given by the Lorentz mean theory. And this was also, we said that, a scattering by a spherical particle is described by this theory. And we basically, in order to quantify scattering, we advocate a parameter which is called the Me parameter, which is basically nothing but the non-dimensional diameter, which is given as a pi dp by lambda, where dp is the size of the particle and lambda is basically the wavelength. And this is a function of the relative refractive index. Okay? So the scattering is characteristics we saw in 3 ranges. When the particle size is really small, this particular zone, we get what we call the Rayleigh scattering. In the middle zone, which is from about 0.2 to about 10, we get what we call the Me scattering. Remember, this is for a lambda of 488 nanometer. And in the geometric optics range, when the particles are really large, you get a very large, intensity. So Rayleigh scattering is by far the weakest. And it should be also mentioned that it depends on what scattering angle you are actually monitoring the signal or quantifying the signal. All right. So this is the Me parameter. This is the particle diameter. This is the intensity. All right. So this is the basic premise which we already did. Then we also did something which is called the interaction points. For example, when there is an illumination, you get a shadow, and then you get the refracted background light, which is given as a bright spot over here. This is also done. And then if you shine a laser now, you get further spots This is with background and laser illumination. And if you recall that this was the first glare point, first order refraction, and this is the glare point for reflection. So this is how it happens, and this is how the first order refraction actually takes place. So you are just shining a laser. This outline is just for, visualization purposes. That outline does not exist. You just see the glare points, okay, when you shine a laser, a monochromatic radiation. Now, when you actually do an illumination like this, and there is a certain angle at which you are receiving the scattered signal, so one can see that this is the first incident point of first order refraction. This is the glare point, and this is the incident and the glare point of the reflection. This is also something that we covered. So if you now have a series of monochromatic incident light, which is incident on a particle, and this is the surrounding medium. So the geometric optics describes the light scattering from small particles using the laws of reflection and refraction. The assumptions are made that the particle is spherical and the light is monochromatic. So then we found out that Snell's law and Fresnel's equations can be used to compute reflection and transmission angles. You can see if this is an incident light, part of it gets reflected, part of it enters. This is the first, what gets out is the first order refraction. Part actually goes out and then it comes out to the other side, which is second order refraction, and this continues for a while. All right. And this is the signal that you receive, and this is diffraction and reflection. Remember, this is the Brewster's angle, and this is the total signal that the phase Doppler anemometer will actually receive. This is what we are going to talk later. Okay, this is first order refraction. The first order refraction, as you can see, so this is the reflection curve, this is the first order refraction. So you can see that this is the region where phase Doppler usually work. We will come to that why it works in that particular region. Now, if you look at from a geometric optics point of view, there is an incident wave, and then there is reflection, diffraction, first order refraction, second order refraction, third order refraction, all these things and other scattering modes. And in some certain modes actually interact with each other, giving rise to interference fringes. And that is exactly what happens. This is light scattering by small particles. So there is, parallel polarization. Okay, as you can see over here, this is for parallel polarization. So there is, you can see reflection, you can see first order refraction, third order refraction, so long and so forth. And this is for the perpendicular polarization. Recall what we did for perpendicular polarization was the S polarization essentially. So this is actually the Brewster's angle. This is the scattering angle. So it is just opened up. So the entire polar coordinate has been opened up. And so at different scattering angles, you will get different dominance of the different modes. For example, at this particular angle, you will get first order refraction mostly, and a lot of reflection as well. But if you go to other modes, you will see the dominance of some other stuff as well. Okay, so this is how these things actually work. Okay, so this is the dependence on relative refractive index. So for example, if it is water and air, if the droplet is say water and it is in an air medium, it is fairly easy, but this curves actually depend on the relative refractive index also. This also we told. And this is for very small particles, what is like a Rayleigh scattering. This is the kind of intensity in logarithmic scale that you would get. And for large particles and even for medium-sized particles, you will get this. So forward scattering, we told, is way larger than backward scattering. So this is how this is all known to you. So now we go to the principles of phase Doppler measurement technique. Now that we have a little bit of a prelude of what we did earlier. So let's look at this. So this is what phase Doppler actually looks like. It's a little complicated, as you can see. So you can see there the initial thing is the same as laser Doppler. So you have a laser light, there's a collimator, and then there is a beam splitter. You split the beam into two, and they are at an angle, inclusive angle of theta. They are made to converge at a particular point, which is exactly what we did for LDV. And then you have two detector probes over here, which are basically off plane. So this two detectors are positioned out of plane of the incident beams, okay, at an angle which is usually called the off-axis angle of phi r. So this is phi 1 and that is phi 2, so this is like the phi. And the detectors are also placed symmetric out of the YZ plane. If you look at the YZ plane, so it is placed out of the symmetric out of the YZ plane by an angle of psi, which is psi 1 and psi 2. Okay, so this is the arrangement that we are talking about. So, and we will see more about it in a little later. But this is the basic arrangement, that you have a laser which basically does the same thing. Up to this is exactly what your LDV actually does. But then now you have two detectors which are basically placed off axis, okay, out of plane essentially. Okay. To know about it in more details, you see this is what happens. So these are the two beams which have an included angle. They are made to converge at that point, which is the measurement location. These are the droplets of the particles which are passing through it, either upward or downward. Okay. Now, this two detectors, if you see, which is U1 and U2, okay, they are placed at the same scattering angle, okay, but they are placed off axis. They are placed off axis. They are placed off axis scattering angle, okay, and they are also at a certain elevation angle, which is psi. So they are at an elevation, so they are moved from the axis, okay, at a particular angle, whatever is that angle of your choice, which is this phi that you see over here, and then they are also elevated from the plane. So that is the thing that you should kind of remember. And then theta is of course the beam intersection angle, and m is the relative refractive index. So if this is the droplet, this is like the meridional line connecting the two poles essentially. So if you so what are you going to monitor, okay, for a small droplet? If you just look at the droplet, if you zoom in, okay, you can see that a part of the light actually goes through the droplet in a certain way, and the part goes in a different path length. So the direction, so it gives rise, when it reaches the detector, it gives rises to this interference fringes. And if you have a larger droplet, this is well indicated. So the light which is entering here gets first. This is first order refraction, and this is also first order refraction. Both of them pass through the droplet, but essentially they actually have a path difference between them. So when the path difference is small, the fringes are basically a little further apart. Okay. When the droplet is actually large, the fringes are actually closer. Okay. They are actually closer. So this is what you see in this particular case. Okay. So this is a small particle. So if you just look now from the top view kind of thing, you will see that this is what the detectors actually see for a small particle and for a large particle. Okay. So this is the superimposed waves from the two glare points. Okay. So because these are the two glare points that you can see over here, right, from the two beams. Okay. Now, if you know the distance between the two glare points, you can also, that is related to the diameter of the droplet, because as you know, the smaller droplets actually have very low spacing and between the fringes. Larger droplets has higher, but so this gets reflected in the spacing of the fringes that you are supposed to get at the detector site. So there is what we call a phase shift, which is denoted as delta phi, which is the phase shift that is measured by these two detectors. So it is the phase shift between these two detectors. What does it do? Okay, let's look at it carefully. So the phase shift, if you are observing the reflection mode only, so if you look at the two signals, you will see that the red is from the one detector, black is from the, or black or blue is from the lower detector. You can see that their frequencies kind of match. They are at the same scattering angle. The frequencies match, but their phases are off by a little bit just because of the path difference. Okay, just off by a little bit. Okay, you can see that they are off just by a little bit across the board. So this is the time, this is the signal amplitude. So remember one thing that just to clarify, that one can technically measure the fringe spacing and infer what will be the diameter of the particles. But the point of concern over there is that the fringes are moving at megahertz. As a result of that, camera monitoring, imaging the fringes and making sense out of it, or basically finding diameter out of it at that high speed, which is of the order of megahertz, is not possible. So because the fringes are moving, remember these fringes are actually moving. And because these fringes are actually moving at that megahertz and with the particle, now in order to measure the glare points, or if you want to measure the glare points or the distance between the two fringes, it's virtually impossible. So we do the next best thing. We put two detectors and measure, because they are at the same scattering angle, we measure the phase difference between these two detectors. Okay, the phase difference that is measured between these two detectors, that is a much easier proposition than measuring, the fringe spacing, which are moving at a very high frequency. So to avoid that, you do two detectors and you measure the phase difference between the two. Okay, but technically, as we can see, by measuring the glare points also, you can measure what will be the droplet diameter. That is possible. But here also, by watching the fringes, okay, you can also find out what will be the droplet diameter. Technically possible, but practically it's a little bit onerous. So what happens is that if you now do a little bit of math, you will find that when you are talking about the phase difference between detector 1 and detector 2, this is the relative phase difference. Okay, so because the lights are coming and then here it is giving rise, these two beams gives rise to a fringe here and fringe there. So, and these are the two, basically the Doppler bursts that you see. And so there is an enveloping function and then there is this oscillating function. So what happens is that you measure, you see the two profiles, the frequencies are the same. It is just there is a phase difference between these two. Now that phase difference is, if you look at it, is directly, it's linear to the particle diameter, which is dp. And then there is a long term, which is a function of, say, cos psi, which we know because this is how we have placed the detector. We know the laser beam diameter, half the angle. And we also know, cos phi. Phi is how much away. This is basically the scattering angle at which we are basically monitoring it. So if you are dealing with reflection, you can relate the phase difference that you see between these two signals, and you can relate that to the droplet diameter or the particle diameter, so to say. Okay, because all these parameters are known, you don't even need any calibration. If you do first order refraction now, you get a very similar thing. It's also linearly proportional to dp, but then you get the relative refractive index. Okay, and in this case, the glare points lies on the meridional circumference of the droplet, which is shown over here. This is this line. It lies on the meridional circumference, the two glare points. And again, you see whatever is within these, square root terms is a function of psi, phi, theta by 2. All of these parameters are actually known. Okay, so the relative refractive index is known. You also know the beam intersection angle, you know the elevation angle, you know the scattering angle, and you know the phase shift. This is what you are measuring. Okay, and these are all given. This is what, when you are assembling your setup or your tool, you actually know all these parameters. Okay, so the linear relationship results between the phase difference of the signals between the two detectors and the particle diameter. As a result, you do not need any calibration per se. Okay, so calibration is not needed at all. Now, you see that when you are getting these kind of, we will come to this in a second because there are certain things that you need to know. So just a recall that you have the two Bragg cells, which introduces the frequency shift also. So in this way, you know the frequency, which gives you a measure of the velocity, and you know the droplet diameter. Okay, so both of these things are actually known. Now here you have to look into one thing over here, because you have derived it for first order refraction or reflection. So you have to monitor it at an angle where the majority of the contribution comes from that particular mode. So you cannot be in a region where all the modes contribute, because in that case, this relationship will not remain exactly like this. So the math is even more turdy, and then you are going to have a little bit more terms, more complications to evaluate. So in other words, the best to avoid is to have a scattering angle predetermined for a particular value. This is, for example, water in air. So you can watch it, you can do it at a particular zone in which the particular mode is dominant. For example, if you do it here, these are the zones which are marked over here. If you do your measurement here, for example, okay, you will find that the contributions from the reflection is like 2 orders off, and the others are even lower because this is on a logarithmic scale. So here most of its contribution probably comes, this is for perpendicular polarization, most of the contribution perhaps comes primarily from a particular mode. Similarly, when you do parallel polarization, for example, you see that this is first order refraction, for example. So if you monitor somewhere here, you are at least 10 times higher than the reflection mode, and you should be good. Remember, you also need to monitor it closer to within the 90 degree, because as you know, the forward scattering is more dominant than backward scattering. So you always want to be here in these zones, okay, mostly in these zones, so that you can actually take measurements and you can infer, and you have to see where the next higher mode is kind of off by 10, here is off by 100. So accordingly you choose your mode, and this is given for a particular M, for a particular relative refractive index. It will vary if you change the refractive index. So the choice when you try to make your setup in which you have the laser beams enter into a particular measurement volume, now the angle at which you are going to measure it from the other side, that actually matters a lot, whether it is like head on or whether it is what angle it is determined by these scattering orders and the dominance of the scattering orders. And you have to choose one of this mode which is well separated so that you can use one such relationship. So that is the whole point. And remember, this is the meridional plane or meridional circumference that we are actually dealing with over here. All right. So this can be further translated into these kind of maps. So for perpendicular polarization, for example, as you can see, so these are the angle of total reflection, the rainbow angle and the critical angle. So you can see the different where the modes are kind of dominant for perpendicular polarization. So you can see in one case this is dominant, this is 2, okay, and this is like 1. And similarly, if you go for parallel polarizations for different scattering angles, you can see the different zones at which there is a dominant scattering order, which is like greater than 90%. So one order is like 90% more than the other order. So the linear relationship therefore assumes one scattering order is dominant. This can be assured by proper choice of the scattering angle depending on the relative refractive index. The figures, the contours lines of 92%, 94%, 96%, and 98% actually gives you the dominance of one scattering order for particles in the range 64 to 1290, which is 10 micron to 200 micron for water, which has a M of 1.33. So this is just a selection matrix or a contour or a regime map where you can park your measurement and you can make sense that what is going to be the case. All right. So this is the selection of your detection angle is therefore very important for you to apply these kind of relationships over there. All right. So the idea is now, how do you realize this phase Doppler technique? Because there can be standard system, there can be planar system, so there can be dual mode system. So in the next class, what we are going to do, we are going to look at that. But in this class, what we did a review of the scattering of light from spherical particles, and we looked at the principles of phase Doppler measurement technique and how the phase difference is important, because you cannot really measure the fringes, which are actually moving, or the difference in fringes that comes because of the particle, that is almost impossible, just because they are moving so fast. Okay, so you put two detectors where you measure the phase difference, and the phase difference is now linked with the droplet diameter, depending on what scattering angle, what elevation angle that you have chosen, and what is the relative refractive index of the medium. For reflection mode, obviously, the relative refractive index does not, or refractive index does not enter into the picture. It only enters into the picture when you are actually dealing with first order refraction. But whatever it is you have to use, you have to go to this graph and basically choose where one mode is dominant to the other, or you use something like this, which people may have done already for a particular fluid and for particular, mean scattering parameters. Okay, so you choose according to that, and then you accordingly park your measurement. See, this is given for a fairly large size range, which is also important, because in your measurement you can have polydispersed droplets or particles which has got a size range dependence. So you really need to choose your scattering order so that it caters to a wide range of particles. So this is something that a priori, or maybe your theoretical calculations has given you the basis that this will be the dominant size range that we are actually looking at. Okay, there is no calibration requirement because of the linear dependence, and because all the other parameters are actually known. The setup looks strikingly similar to an LDV. Okay, except now that you have two off-axis detectors at elevations, so that you can monitor the phase difference due to these particles, and then you measure the phase differences, basically looking at curves like this is what you look at. The frequency is already related to the velocity shift now, that is to the diameter. Thank you.